So, good afternoon. I see a lot of familiar names already joining. Many of you probably don't know me. My name is Giuseppe Catanese, and I'm one of the forecasting specialists at CCmath. Welcome to this webinar of today. The argument will be dealing with overfitting, how to avoid forecasting noise. First of all, let's have a look at these two graphs. In these two graphs, we see on the axis, we see the time, and the actuals are related to the number of calls that the call center received at some times. So we see the number of calls received by this call center at 9 o'clock, at 10, at 11. What we see there are basically then the actuals, which are represented by the blue line, and the yellow line is the fit. What was the aim of doing all of this? The aim was to make a forecast. We wanted to forecast the number of calls that the call center would receive at that day. So now the question is, you see these two graphs, they represent two different models. So I have access to the chart here. I can see. I want to ask you, which of them would you choose? The first or the second? Which of the two you think is a better model? Sorry, yes, I was mute at the beginning. Now I speak. You can hear me? Okay. I see people answering, so it means you hear me. Okay. First, yes, exactly. The first one is the best. And we see that on this data, the first model achieved a 23% of WAPE, and on the second, a 33% of WAPE. But how comes that someone can do such a bad performance on the second? How did it happen? Basically, the second graph was and this is what we will talk now. Basically, they used the pattern of the previous day to estimate, to try to forecast the pattern of the next day. We have here the WAPE, which is an accuracy estimator, basically an accuracy measure. It's called, the WAPE is the weighted absolute percentage error, but we could have used anything else, the mean squared error or average percentage error. Here we use the WAPE. Basically, the second graph was doing a WAPE in the training set of 0%, but the second of 23.5. So the guy was confident, saw a really good fit, and thought, maybe I can use this pattern to do my forecast. But actually, this did not work, since if you just copy the past in the future and you plot your previous graph, what you see is that you achieve actually a worse WAPE, a worse accuracy. And this is basically what happened. The training set was relative to a day. The previous day, basically. Just the previous day. It was copied in the future. It is really important to understand overfitting, the concept of signal and noise. When we listen our favorite song, we likely don't hear only the music, for example. We hear the neighbor's dog, the fan, your partner talking at the phone, and at the end, you hear your favorite song. What we do is normally we try to pay attention only to the song. Sometimes the neighbor's dog will bark louder than the song, but this doesn't mean that bark of the dog is part of the band of your music sound. What you normally do when you do any activity is you try to focus on your activity and you try to not see the other things. Ideally, we would like to do the same every time when we estimate a model. We want to basically to focus on what is the signal and take the other things out of our attention. In this case, it's like we want to, in this case, the process underlying your actuals is the signal, and we would like to take out any noise from this. Then we go back to the question, what is then overfitting? According to Wikipedia, the production of an analysis that corresponds too closely or exactly to a particular set of data and might therefore fail to fit additional data or predict future observation reliably. This in general happens when the model learns too much noise in the training data. Conversely, an underfitted model is not learning enough signal. If we go back to our previous example, we really understand what is the signal, what is the noise applied to the data. Basically, we see that in the first graph was mostly detected by the model. This is a nice model that was used in our software. It's a sophisticated algorithm which tries to take out the noise. But in the second graph, what we see is a model which overfitted and contains noise. So this is exactly what we mean by saying what is the signal in a data set, in a process, and what is actually the noise. So it is really important to avoid disasters because let's see, for instance, at this model. What we see is that the model is overfitting, in this case, the seasonality. We see that in the week 2 of the 2018, there is a peak. And there is some missing data on the week 46 of the 2017. If we look at the second part of in the forecast, see, okay, sorry, yes, this was basically it was divided between training set and test set. At the left, we see the fit, and on the right, we see our forecast. We see that the forecast is actually copying what happened in the past. The forecast is the yellow line, and the dotted line is the fit, yes. Sorry. See that the forecast is copying exactly what happened in the past. And this is exactly what we want to avoid. This is because estimating a model doesn't mean just copying what happened or fitting a model that represents too closely what your actuals are. This is a model when it's correctly specified. We see that the algorithm ignored the outliers, ignored data points from where we don't have evidence to believe that they were part of the seasonality. The data point, for instance, in the case of week 46, we have missing data points. And the algorithm mistakenly thought that this was 0. By the way, I forced the algorithm to overfit the seasonality in order to show this, basically. While in the second case, I used automated settings, which filter out the noise. But this is the principle. The principle is that you don't have to copy the past. This is overfitting. But how can we prevent overfitting then? Because often we don't have so many data points, and we sometimes don't know how to do better. There are ways. There are easy ways, but there are also more technical ways. An easy way to prevent overfitting is to add more data. This comes from a statistical theory that says that basically, imagine that you have infinite data points. In that case, you would be able to find exactly the process of your data set. But the problem is that we never have so many, of course, we don't have infinite, but also sometimes we don't have in call centers more than 3 or 4 years of data. You likely want to estimate your model using only 1 year or 2 years. And this is tough. So what you can do, generally speaking, you can add more data or reduce the number of inputs. What I mean by this, let's assume you want to estimate your seasonal pattern. You are using 12 months of the year. You want to see on average how many calls you received on January, how many calls you received on February, how many calls you received on March. But if you use all 12 months to assess this, you might overfit. You could group them. You could say, let's see the summer, let's see the winter, how many calls I received during the summer, how many calls I received during the spring. This means reducing the number of inputs. Or instead of saying, let's see how many volumes I receive on Monday and how many I received on Tuesday, you can say, let's divide my days between working days and closed days. Maybe your call center is not closed, but likely you have a different number of volumes during the weekend. Then there are ways which are more technical. People who use machine learning, they use a technique which basically they stop the training phase of their machine learning algorithm earlier than normal. It's a little bit advanced because first you have to know how to use a little bit machine learning, but then you also don't know when to stop the algorithm. Another advanced technique is the one to add a regularizer to the loss function, which is what we do in CCmath in our algorithm. It's called spline. We basically use a regularizer to the loss function in order to smooth the pattern. We see that on the left, the pattern was really noisy, and then using this technique, we smooth it. Let's go at our specific topic, which is as about brought in the ads to my title, events. What about overfitting in events, in marketing events? Events are significant when are part of the signal, but there are various methods to detect significant events. An easy way is the one to look at the graph. This works really often, but it has some. It's not super correct in a statistical point of view, but it's already something. It contains some reasoning, and it avoids that you do just guessing. And then we have hard ways. One hard way is a statistical test. And another one is splitting the data between training and test. So basically, you assess the performance of your model on the test set. Let's look at the simple way, which is inspecting the graph. Basically, you can exclude the days. There are some steps before inspecting the graph. The first step is to exclude the days with events and then to compute the fit. In this case, our fit is the average. You see the orange line is the average. This is the fit, and this is basically computed after taking out the events. Events are, we have event A and event B. At the beginning, we take these events out, Then we do the average, and this is, or we can do also a moving average. And this is basically becomes our fit. What you can do is to compare. Is it really important? You know already that you have an event A, and you know already that you have an event B. So what do? Is that you go where the event A was happening, and you see the distance between the fit and your actuals. This you see that this has, of course, an impact. Then you look at event B, you see that these events are also an impact. But it's really important. You have to see if these events are really far from normality. And what I mean for normality, for normality, I mean these all the other actuals, the actual where you are sure there are not events involved. Here there is lower and upper bound. I use a statistical technique to draw them. I use standard deviation. But this is to show you the fact that a real event is far. It is really far from the fit. And first, what you can do is to assess if this holds true or not. So consider whether events behave the same way also in other part of the data. Let's see at this example. We have event A, we have event B, but also we know again that we have a second time that the event B will happen. I hope this is clear. For event, I mean, can be a marketing campaign or can be anything that you think your actuals will be higher or lower than the normality. This is what I mean by event. And normally you can give a name to the, normally you know when an event happened. Maybe next week you will have a marketing campaign, or in 2 weeks you will have a marketing campaign. It is important that you look at the graph when this event happens, and you see if what you are thinking in your reasoning that the event will have an impact is actually true, so that you see it in your graph. So let's see in this case, for instance, you know that there is an event B, and you think this event has a negative impact, for instance. But then when you go forward in the future, you see that this event B happened again, and you see that the impact looks actually positive or looks nothing. Then you should start questioning yourself, your reasoning, and think like, okay, maybe it's better if I don't really add this event B. I have another example. Let's assume that the event that we called B is actually event A. So in the future, event A happened. The one that I called before B now is A. So you see, it's a little bit far from the normality. It's positive. I was thinking that it has a positive impact. Then I see this event again in the future. I see that it has a positive impact. And then I think like, what I think, shall I insert it or not? Since now at least you see that this event behaves the same in other part of the data, this event has the same direction of impact, so you can be more sure that this event is actually significant. It is less likely that this event can be caused by chance. Not like the previous case of event B. See, event B before we thought was negative, and now it's positive. After that, we decide, because as we say, that this method is a little bit deciding. After we decide that an event is significant, how do we forecast it in the future? what we can do is that we see the impact and estimate the average between different impacts, or we can we can apply linear regression, but it's already a good method to make the average against the normal fit, and then we replicate this event in the future. But only after we know that it's significant. Then we go to the training and test set, which is a little bit the more complicated method, the more advanced method. So how does it work? Basically, what you do is you divide your data set between training and test set. You estimate a model, you do a fit, but then normally what would you need is to wait for the actual, but since you already have some data, what you can do is exactly to split it between training set and test set. So you can make a forecast on the training set and evaluate it on the test set. By making a forecast, I mean to estimate a model on the training set and then evaluate the performance of this model on the test set. How can this apply to overfitting and events? Basically, what you can do is to try different combination of events. Before we had an event A and an event B. What you can do is let's see if I set as input only event A, what is my performance on the test set, and then you do a run. Then you can do a second run, looking setting a model only with event B. And then you can do a third run, putting them together, mapping them together. So basically, you try different combination of these events, and you assess your performance on the test set. You tune it basically. When we talk about algorithms, sometimes algorithms have parameters. It's the same principle. You tune your algorithm, and then you assess the performance on the test set. Before, at the beginning of the slide, we did exactly this. We divided our dataset between training and test, and we saw that the model had a bad performance on the test set. This is how we understand that we were overfitting, and we were only copying the past. So according to this principle, what do we do then? We change the parameters of our model, we change the inputs, or we change settings, and we try the model again to see to assess the performance. We saw at the beginning that there was after we specify our model correctly, then our weight decreases our accuracy increases in the test set. In this case, we know that the model is correctly specified. This is a really powerful method, and I really suggest you to do that with your forecast. I finished a little bit earlier than expected, but since it's a really complex topic, I would like actually to answer your questions. Yes, takeaways from all of these that we said is how to prevent overfitting, add more data, reduce the number of inputs, look at the graph, assess performance on test set. If you have any question, you can write it in the chat, or maybe by voice also. What statistical method do you use to smooth the noise? There are different methods to smooth the noise. If you think about even a moving average, smooth the noise, but in CCmath we use a little bit more complex methods. We use We use different types of algorithm. One of our algorithm, for instance, use complex optimization methods, and then there is a regularizer to avoid the noise. So the noise is smooth thanks to a regularizer, basically. This is the statistical method that we use. I'm answering to Benjamin. Hi, Benjamin. You are asking what is, someone is asking what is a regularizer? Okay, I will explain more about the regularizer. So Benjamin, you see these two graphs? In one, we detected the signal, and in the other, we detected too much noise. So it's signal plus noise. In this, we use a technique called the smoothing spline. And the regularizer basically is something that is added to the cost function. For instance, when you do a linear regression, what you do is to find a line that best fit your data, minimizing squared errors. Sometimes you don't want to minimize these squared errors completely. So what do? You add a regularizer to the cost function. And in this way, you basically want to be close to your data, but not very close, too much close to your data. So basically, you are voluntarily and deliberately adding error to your model. This is what the regularizer does. Alex, is this polynomial regression? No, it's not polynomial regression, but polynomial regression is also a good method to smooth the noise. We use a technique called smoothing spline for this model. It's still early, and I would like to talk more. Please, if you have some questions, write in the chat. All right, if there are no more questions, I then thank you for attending, and we will see you next week, Friday, 1st of May at 4. Please, if you have send us some suggestion for next webinar, and I hope you enjoyed this webinar today. Oh, there is a question. Giuseppe, how do you create test and training set? Basically, hi Catherine. Basically, to create test and training set, what do? Is you split your data. Imagine you have 100 data points. So there are different ways to divide your data between training and test set. Really different methods. One method is the one that, for example, you have 100 data points. So you use the first 70% for training, and then the last 30% for test. In this way, you can try different combination of your parameters and see which one is the performs best. There are more complex methods that we were not going to assess today, but also there are methods for training and test set that you can sample randomly data points in your data set, and then you can test on random data points in your data. Thank you, guys. Thank you. It's a little bit strange to don't hear myself, but to don't hear feedbacks or. Okay, thank you, Santiago. Thank you for your topic. There is a question from Benjamin. Do you have a method to quantify how much noise is in the data for knowing how variable the income volume is? You could estimate the variance, but that would not. There are different measures of variability. But the problem is that before understanding the variability of your data set, you should first detect the signal. So you can, the best way is to find a good model. So estimate a good fit, which is only the signal, then remove the signal from your actuals. So actuals minus the fit. So in this way, you find the errors, and then you compute the variance of the errors. This is a good way to see the noise of your data. Maybe more questions? Thanks to you, Benjamin, for the question. Okay, if there are no more questions, thank you very much for attending today, and have a good weekend. Some of you are locked down. I'm locked down too. I'm in Italy at the moment, locked down from for a couple of months already, actually. I wish you a good weekend, and for who is in Netherlands, a good long weekend, since on Monday is the King's birthday. Bye-bye. Thank you.